Hello all, welcome to Chemistry EduHub. Today's topic is aromaticity. This is the most important concept or the phenomenon exhibited by organic compounds. So generally when we say aroma, it is nothing but the smell. But here, aromatic compounds can have the smell, but it is not wholly about the smell. It is about a property where the compounds exhibit compounds that have high degree of unsaturation, and they behave like saturated compounds. So what is aromaticity? It is a property where the compounds with high degree of unsaturation behave like saturated compounds. Such compounds, what do we call them? We call them aromatic compounds, and the phenomenon is called aromaticity. Okay, now benzene is considered to be the parent member of all these aromatic compounds. Now, what is the meaning of high degree of unsaturation? Unsaturation is nothing but the presence of double or triple bond. So when do we have a double or triple bond? Whenever there are less number of hydrogens compared to the carbon atoms in that compound. So high degree of unsaturation is also nothing but the index of hydrogen deficiency. Which also means that the total number of rings and pi bonds present in a molecule. So generally those compounds which have more number of rings in them or more pi bonds in them will show this aromatic behavior. That is the meaning of high degree of unsaturation and index of hydrogen deficiency. Now, how do these high degree of unsaturated compounds behave like saturated compounds? The main property here is nothing but the resonance. What is it? The shift of pi electrons or the delocalization of pi electrons. So, though they have more number of pi bonds, because of the resonance process, they behave like saturated compounds, and this will provide the molecules the stability that they need and the type of reactivity that they are showing. Such property is called aromaticity in the organic compounds. We need to know the conditions for aromaticity, because not every organic compound that has carbon and hydrogen in it can be aromatic. Now we need to look at the conditions for it only to identify which compound is aromatic and which is not. So the first and foremost condition is the compound has to be cyclic, it has to be planar or nearly planar. The first and foremost condition is the compound has to be cyclic. Cyclic is nothing but closed chain or ring like this. So instead of open chain compounds like this, we should have a closed ring. Such compounds are cyclic. And what do you mean by planar? Planar is either the hybridization has to be sp2, or you can identify it as like when all the atoms in the compound are on the same plane, then you call it planar compounds. So the first and foremost condition is it has to be cyclic and planar. Then each atom in the ring, whenever you have a ring, here if you consider all the carbons are sp3. Though the ring is cyclic, carbons are surrounded by all single bonds. When a carbon is surrounded by all single bonds, the hybridization is going to be sp3. sp3 hybridization will lead to tetrahedral, a three-dimensional structure but not planar form. So what is the second condition? Once it is cyclic, it has to be, each atom in the ring must be sp2 hybridized. When can be the carbon in the ring will be sp2 hybridized? Whenever there are pi electrons in the ring. So consider benzene molecule. where it is cyclic and also it has alternate pi electrons, where each carbon in benzene ring is sp2 hybridized. Such molecule is said to be planar with sp2 hybridization and pi electrons. And how this pi bond is formed? It is formed by the unhybridized p orbital. What do you mean by unhybridized p orbital? The p orbital in carbon is not involved in hybridization. It is left free to form pi bond through sideways overlapping. That is nothing but the unhybridized p orbital. Now in this ring, each atom is sp2 and it is formed by unhybridized p orbital, which is allowed for the delocalization of pi electrons. What do you mean by delocalization? They keep on moving. They move from one atom to the other this way. This is known as the delocalization. Now the third condition is delocalization of pi electron cloud should have 4n plus 2 pi electrons. 4n plus 2 pi electrons. This rule is nothing but the Huckel's rule. Huckel is the scientist who gave the structure for benzene, and he only proposed the aromaticity property. So inside the benzene ring or inside any ring, the number of pi electrons has to be equal to 4n plus 2. N is not number of pi bonds here, it is just a integer or it's just a number. So 4, if the n value is equal to 0, so what do we write? 4 into 0 plus 2 equal to 2. If the n value is equal to 1, then 4 into 1 plus 2 is equal to 6. If the n value is 2, then 4 into 2 plus 2 equal to 10. Likewise, based on the n value, we are going to get the 4n plus 2 values equal to 2, 6, 10, 14, 18, etc. So whichever ring with pi electrons has the value equal to 4n plus 2 pi electrons, such compounds are said to be aromatic compounds. Only those compounds which have the pi electron number equal to 2, 6, 10, 14, 18, etc. so on, such compounds are aromatic. I am repeating once again, this n value is not the number of pi bonds, it is just a number 0, 1, 2, 3 so on. Okay, so this is the third condition. So these are the three conditions. The first is it has to be cyclic and planar. Then second is it should be sp2, and the third criteria is pi electrons has to be 4n plus 2 inside the ring. So these all conditions make the compound aromatic. So aromaticity, what it does, it increases the stability of the molecule. Aromaticity is directly proportional to the stability of the molecule. Suppose if a compound satisfies all the 1, 2, 3 conditions but has no 4n plus 2 pi electrons, it has only 4n pi electrons, where the number is equal to 4, 8, 12, 16 so on. If the number of pi electrons inside the ring is equal to 4, 8, 12, 16 and so on, instead of 2, 6, 10, 14, such compounds are called anti-aromatic compounds. Aromatic compounds are very stable, anti-aromatic compounds are unstable. Okay, so if the compound fulfills all the above conditions but has only 4n pi electrons in them, such compounds are said to be anti-aromatic compounds. Now anti-aromatic compounds are unstable and they have paramagnetic behavior. What is paramagnetic behavior? They get attracted to the magnet in a large extent. So they show paramagnetic behavior. So if we look at the order of stability among these compounds, order of stability follows, as we know, aromatic compounds are the most stable compounds. Then comes non-aromatic. The compounds which are not aromatic at all are next stable. Then comes the least stable compounds. These are anti-aromatic compounds. So aromaticity brings the stability in the molecules. Anti-aromatic compounds become unstable, and non-aromatic are more stable compared to anti-aromatic compounds. Let us see few examples for the aromatic compounds. So we have seen the conditions already. The first and foremost best example for aromatic compounds is the benzene. Then we have 2-ring compounds, that is naphthalene with alternate pi bonds. Then we have 3-ring compounds, that is anthracene. These are the most common aromatic compounds with the cyclic rings and planar nature. Okay, so this is benzene, this is naphthalene, and this is anthracene. Then we have hetero compounds also that show aromatic behavior. Hetero compounds in the sense, apart from carbon and hydrogen, there could be other hetero atom like nitrogen or oxygen or sulfur. Okay, so let us see examples of them. So pyridine is an hetero compound that has aromatic behavior. Then there is oxygen in the ring, that is furan. This is furan, this is pyridine. Then sulfur heteroatom in the ring, that is thiophene. Wherever there is sulfur, we use the term thio. So this is thiophene. Then we have benzofuran, indole, imidazole, pyrazole, etc. There are many different aromatic compounds. Now there could be ionic species also that behave like aromatic compounds. What are those ionic species? The 5-membered ring with a negative charge. So here if you consider, this single pi bond indicates 2 electrons, this indicates 2 electrons, and the negative charge also indicates 2 electrons. So hence overall in the ring there are 6 electrons. This follows the Huckel rule. Similarly, there could be 4 carbons in the ring with 2 negative charges. This also indicates 6 electrons inside the ring, which undergoes delocalization. So there could be 7-membered also, 1, 2, 3, 4, 5, 6, 7 with a positive charge and alternate pi electrons. Positive charge indicates no electrons, so obviously this has 6 electrons. Such ionic species also can be aromatic. Annulenes are another example for aromatic compounds. These annulenes are nothing but they are carbocyclic. That means they shall have only carbon and hydrogen in the ring, and they are monocyclic. Monocyclic in the sense, how many ever carbons are there, they form only one single ring. Such compounds are called annulenes. Suppose if you look at 4-membered ring with a alternate pi electrons, such compound is called 4-annulene. We need to look at the number of carbons. So 1, 2, 3, 4, it forms 4-annulene. Similarly, there is 6-annulene, that is benzene. So 6 we write it in square brackets, or we call it parenthesis, and we write it as 6-annulene. So the other name for benzene is 6-annulene. Then we have 14-annulene, that is this way. These are a bit complicated structures with alternate pi electrons. So this is considered to be the 14-annulene. So this has completely carbon and hydrogen in it, and this whole thing is considered to be the single ring. So hence it is called 14-annulene. Then we have 18-annulene like this. But the exception in this is 10-annulene. 10-annuline, except for 10-annuline, rest are all are aromatic, but 10-annuline is anti-aromatic. It's because of its structural arrangement. Let us see that. 10-annuline is written this way, where you will have alternate pi electrons like this, but because of the arrangement of hydrogens in this ring in the opposite direction, this molecule is becoming non-planar. This molecule is becoming non-planar, and hence the molecule is non-aromatic. Rest all annulines are planar and aromatic, except for 10-annuline because it is non-planar due to the repulsion between the two hydrogen atoms. Because of the trans arrangement, there is a strain in the molecule and these two get repelled. Because of that, the molecule is becoming non-planar and it is non-aromatic, but the rest all are aromatic in the nature. Let us see a few examples for anti-aromatic also. So whichever has 4 and pi electrons in them will behave like anti-aromatic compounds. So this is the cyclic ring with 4 carbons and alternate pi electrons. So this has 2 pi bonds, which is equal to 4 pi electrons. There could be ionic species also in the anti-aromatic compounds with 3-membered ring, 1 pi bond and 1 negative charge. So this also indicates 4 electrons in it. And then we have a 5-membered ring with 2 pi bonds alternately and the positive charge. So this also is equal to 4 pi electrons inside the benzene ring. And here you have a heteroatom, that is boron. Boron is an electron deficient species. It has no lone pair. So only these 2 pi electrons will be involved in the delocalization. So it leads to anti-aromatic behavior. So this is the complete video related to aromaticity and the type of compounds. Thank you.